start off, we'll give a definition of fatigue. Fatigue is a form of failure that occurs in structures subjected to dynamic and fluctuating stresses. This fatigue is the largest cause of failure in metals, surprisingly. Also, fatigue is brittle-like in nature, even though it applies to normally ductile materials. Different types of load that fatigue can have include axial, which is tension and compression loads, flexural, which includes bending, and torsional, which is twisting. The plot shown below is a variation of stress versus time fatigue failures, and it can be analyzed. Okay, so the stress versus time curve can be analyzed using equations that relate the average to the max and the min, which would just be the max plus the min divided in half. The range of the stresses could be analyzed using the max minus the min. Also, we've got an amplitude, which will be 1/2 of the range. Key points: the stress ratio also, which is the min divided by the max, can also be obtained from the stress versus time curve. The key features to this can cause failure even though stress max, is less than stress y, responsible for 90% of the mechanical engineering failures. This is fatigue. Our next topic will be the SN curve. The SN curve. This was developed through laboratory simulations tests that involved rotating and bending along a beam. Repeating this procedure multiple times gave us a variation of data points, and then this stress was plotted against a natural log of the cycles for each of the different specimens. This is taken as either the amplitude, which we just defined earlier, or the stress max. The higher the stress, there was also less cycles to failure. For some iron-based and titanium alloys, the SN curve has a fatigue limit, which is shown. This represents the largest value of fluctuating stress that will not cause failure for an infinite number of cycles. Usually it's between 35 and 60% of the tensile strength. Shown below that plot is a plot that has fatigue life and fatigue strength. Most non-ferrous alloys do not have a fatigue limit. Instead, they have a fatigue strength that corresponds to a certain failure point or cycles of failure. Now we're going to apply the fatigue behavior to a problem. We're going to compute the minimum specimen diameter to yield a specified fatigue lifetime for a tension compression test. In this given problem, there's a cylinder of brass which has a load amplitude of 10,000 newtons. The minimum diameter, we want to find the minimum diameter to ensure fatigue failure not to occur at 10 to the 7 cycles. And assumptions that we will make is we want a factor of safety of 2.5. Our first step to solving this will be using either figure 8.20 in Callister or using a maximum stress versus cycles to failure curve. And we can obtain the stress that corresponds to 10 to the 7 cycles, which this value will be 115 megapascals or 115 times 10 to the 6 newtons per meter squared. Our first step to solving this, after obtaining the corresponding megapascal value, is noting that stress will equal force divided by area. Area in our case for a circular bar will be pi over 4 d naught squared. Combining these two equations, we'll get the following in step 3, which is stress equals 4 times the load divided by pi d naught squared. Solving this equation for the diameter, we will obtain that d naught is going to be equal to the square root of 4f divided by pi times the stress over n, where n is the factor of safety. And the last part of this is to plug in the knowns. So we will get d naught equals the square root of 4 times 10,000 newtons divided by pi multiplied by 115 times 10 to the 6 newtons per meter squared divided by 2.5. Doing this will then give us a value that is equal to 16.6 millimeters. Following this discussion on the rate of fatigue crack growth, crack grows incrementally as shown below with the equation. We have dA over dN, which is the crack length per loading cycle, the differential of it. This can be applied to rotating shaft. The crack grew even though Kmax is less than Kc, and the crack will grow faster as the stress increases. It'll also get longer and the frequency will increase. These pictures show the origin of fatigue, which is typical. To improve fatigue life, we can impose compressive surfaces. This includes shot peening and carburizing. Carburizing is where we take carbon and we inject it into the interstitial sites, and this creates a compressive surface. Also, shot peening is very, very similar to that, other than we're using another element compared to carbon. Some things that can improve the resistance to fatigue of a metal alloy involve improving the surface by finishing it with polish, also reducing the number of internal defects, eliminating sharp surface discontinuities, and lastly, case hardening.
Now we can talk about creep, which is another method of mechanical failure in a lot of materials. Creep originates from static loads that are maintained at elevated temperatures in the material. They're time dependent, they're permanent, and they're undesirable, and they often act as limiting factors for the lifetime of a part. They're observed in all materials, but we look at them a lot in metals. And in metals, the valuable temperature at which creep takes place is about 40% of the absolute melting temperature of the metal. And it also occurs significantly in amorphous polymers like plastics and rubbers. So this graph is creep strain versus time, and it shows three main sections that we like to look at. The first is the primary creep, which the strain, the beginning of the primary creep regime starts just after the instantaneous elastic deformation that takes place when the load is applied at the sample. The primary creep displays a decreasing creep rate, and that's a result of the creep resistance increasing by strain hardening in the material's microstructure. So what that really is basically the material is getting cold worked as it's being strained, and that causes it to resist that strain more and more. The secondary regime of the graph is secondary creep. The slope of this is called the minimum steady state creep rate, And there's a balance in this regime between the strain hardening and the recovery, and that gives us a more linear section to the graph, because at the elevated temperature we're seeing recovery of certain grains and crystallography at the microstructure, but at the same time we're also work hardening the material as we're pulling it apart. In the third section, the tertiary section, there's an acceleration in the creep strain versus time, and that acceleration takes place to rupture, which is denoted by X. And this usually microstructurally, we see a lot of grain boundary separation, cracks and cavities and voids are forming. So really all these are our stress concentrators that contribute to the rupture of the material. On a similar note, this is the region where we'll see necking in a material, if that's going to happen. So this is the superposition of three different creep strain graphs performed at different temperatures, and as we can see, the black arrow denotes increasing temperature in its direction, and it shows us that creep strain rate increases with increasing temperature, which makes sense because it's a thermally activated process. I'll try. So as we know, the secondary creep portion of the creep strain rate graph is important for several reasons. It's termed the steady state creep rate, and that's given by the slope of that graph on the previous slide. And there's another way to calculate the strain rate, the steady state strain rate at this point, and that's given by the equation on this slide, where K2 is a material constant, sigma is the applied stress, N is the stress exponent, which is another material parameter, just like K2, K sub 2. Q sub C is another material parameter. It's the activation energy for creep. R is the gas constant, 8.314 joules per mole kelvins. And T is the absolute temperature in Kelvin of the material. And we can see from the graph below the equation that strain rate increases with increasing temperature or increasing stress, which makes sense because those are the two parameters of loading and an atmosphere that we're looking at for these materials. So in order to use some of the concepts of creep, we can look at one of the homework problems that we actually did, which is 8.43 in the book. And we're given some data for steady state creep at 140 megapascals, where in the first scenario, the steady state creep rate is 6.6 times 10 to the negative 4 per hour at the temperature of 1090 Kelvin. The second is 8.8 times 10 to the negative 2 per hour at 1200 Kelvin. And one of the material parameters mentioned before, N, is 8.5. So what we need to do is find the steady state creep rate at 1300 degrees Kelvin for a stress of 83 megapascals. So I put the equation again on this slide so that we can look again at those variables and see how they fit together. And below, all we've done really is plug those numbers that were given, the gas constant, the temperature, the stress, and the steady state creep rate into two different equations, and we establish a system of equations by doing that. With these systems of equations, we want to use natural logarithms because we have an exponential on the right-hand side, and what that allows us to do is kind of bring everything onto one level. And then what we can do, since we have a system of equations and two unknowns, is we need to solve for Q sub C, which is the activation energy for creep in the material, and we also need to solve for K sub 2, which is just a material parameter, and we can do that as shown in the bottom portion of this solution. So as we continue solving the problem, we find that the activation energy for creep in the material is 483,197.8 joules per mole, and we're actually just going to take the decimal point off of there moving forward just to kind of simplify calculations. We plug that value back in to the expression that we found before for ln of K sub 2 and find that K sub 2 is 5.56 times 10 to the negative 50. With those two values, 483,197 joules per mole and 5.56 times 10 to the negative 50, we can use the information given at the beginning of the problem that T is 1300 degrees Kelvin given in the exponential on the far right, and that our applied stress is going to be 83 megapascals, which is also 83 times 10 to the 6 pascals, and that's in the center of the right-hand side of the equation. And we also have that n, which is our material parameter, which is the stress exponential, is 8.5. With those, we find that the steady state creep rate is 4.37 times 10 to the negative 2 per hour. So now that we've looked at the secondary portion of the creep strain rate graph, we can look at what happens microstructurally in the third portion, which is the tertiary portion of that graph, where we saw an acceleration of the creep strain rate up to the point of rupture. We mentioned before that during that time, a lot of stress concentrators start to gather in the material, like voids, cracks, cavities, and grain boundary separation. And so we can see in this image here that the applied stress is a tensile stress, and it's uniaxial, going from the bottom of the graph to the top of the graph, or from the center to both top and bottom. And we can see through the arrows pointing at them, and also through just kind of looking at these voids that are forming, these black sections in the graph, that along the grain boundaries we're seeing a lot of splitting and rupturing, and that's what's going to cause that material to fail. So we can kind of summarize the entire Chapter 8, even though we only went through a couple of the last sections. But the whole thing's on failure, and we can kind of work with that in general. The first point is that engineering materials are not as strong as they're predicted by theory. And the reason for that is because flaws act as stress concentrators that can cause failure. That stress is lower than theoretical values, and those are the stress concentrators that we talked about, like grain boundary separation, voids, cracks, and cavities, and some of those concepts are mathematically introduced earlier in the chapter. And the same goes for sharp corners that produce large stress concentrations in premature failure. Those are also stress concentrators. So a lot of failure type depends on temperature and or stress applied. For simple fracture, where the temperature is less than 0.4 or 40% of the absolute melting temperature of the material, and is non-cyclic, so it's not being repeated or applied at measured in even intervals over a long period of time, failure stress in those circumstances will decrease with an increased maximum flaw size. So the larger the void, basically, the failure stress will decrease. It'll be a weaker material. Also, if we do something like increasing the rate of loading in the simple fracture, then we are going to see a lower failure stress or a weaker material, or combination of the two. For fatigue, which is the first section of what we examined in our video, which is caused by cyclic stresses, the cycles to failure, or the number of cycles until that material fails, will decrease as the change in the stress increases. So with larger stresses, we see less cycles to failure, and with lower stresses, we'll see longer cycles to failure, which kind of intuitively makes sense. We're using the material less, and so it's going to fail slower, or we're using the material more, and it'll fail faster. For creep, which is at temperatures above 40% of the absolute melting temperature, which is in kelvins, obviously, the time to rupture, or the time for that material to fail, will decrease as the applied stress or the temperature increases. And that kind of intuitively makes sense because creep is thermally activated. So with greater temperature, we'll see more creep. It also makes sense because with increased stress, we'll see more creep. That kind of follows through even from simple fracture. And it mathematically makes sense by the equation given in a couple of slides back, and also by the example that we went through.